Hi, and welcome to this part 5 of our lesson 8 video for novice machinists. And our lesson 8, well, is all about the drill press. Now, this is a bit of a special video because, well, you have to keep with the times, and I'm already behind the times quite a bit. But I received many comments about the fact that I was still in low def. And I commented many times that you really didn't want to see me in high def, but I have to upgrade. So I went out and bought a new camera. I'd show it to you, but it's filming me right now. I got some new software, and well, I pimped out my computer with a new graphic card. So I'm all ready for high definition. Now, this is a quite busy time of year for me. It's syrup time, maple syrup that is, and that, well, is quite time consuming. And well, I've also been spending some time learning how to use the new camera and the new software, and I'm starting to get a handle on that. But I've been busy in the shop also, and as you can see, well, I've made myself a new base for my pedestal grinder, and I've mounted my drill press on a new heavy and very stable base. So there shouldn't be any shake, shimmy and roll anymore when I film up close these machines. Because as you recall in the last few videos, well, things were a little mobile when I was using them. In today's video, we're going to be looking at the accurate positioning of holes. We're going to be looking also at special setups on the drill press, and we're going to be looking at how to increase productivity by using tools such as drill jigs. Now, we're ready. I've shaved for once. I even cut my nose hair because now we're ready. We're ready for high def. So let's roll. So you want to position holes accurately. And the question is, how accurately do they need to be positioned? And that will vary from project to project. But the real question is, what do we need to know? And that is, we need to know 3 dimensions to position a hole properly, and we need to know 3 different tolerances. So what are the 3 positions? Well, the first is X and Y. From reference surfaces generally to the center of the hole. So that would be a dimension in X, a dimension in Y. Now those dimensions require tolerances, and generally speaking the same tolerance will apply to both, but not always, but generally. So we have X and Y with a dimension and a tolerance. So that positions or indicates where the center of the hole needs to be. But that's only part of the picture, because a hole, well, is a cylinder really, and it has a geometric shape. So the hole will have to have a diameter, and the diameter will be given in a linear distance, such as ½ inch, and it will have a tolerance such as plus or minus 0.02 of an inch. So we have 3 dimensions there, X, Y, and diameter, and 2 tolerances. My tolerance for X and Y, and my tolerance for the diameter. What is the 3rd tolerance I was talking about? Well, a hole is a cylinder, so it has a geometry. And there is such a thing as geometric tolerances, and that in this case means how close to a perfect cylinder does my hole have to be. So there's our 3rd tolerance. Now if you've never heard about geometric tolerances, well, we've spoken about those in other videos, and here's some or a video you can take a look at to understand that a little more. Well, now we know what we're shooting for. We're shooting for dimensions and tolerances. But how do we ensure that we're going to attain those dimensions and respect those tolerances? Well, most people would do what they shouldn't do, and that is use the most accurate way of positioning a hole, and I didn't say a hole, I said a hole, on a part regardless of the tolerance they're using, and the logic being, well, if I do it as accurately as possible, it'll have to be good. And that will work, but it is a monumental waste of time. No, the trick here and the art to positioning holes is selecting the proper sequence. So we're going to be looking at 4 ways or methods to approach the positioning of holes. And that's important to say that this is a general overview. You can mix and match these methods to get the results that you want. Now, the first way we're going to look is the least accurate way. And it's a way to position when the positioning X and Y is not very accurate, the hole diameter is not very accurate, and the hole's shape or geometry is not very accurate. Then we're going to be looking at a method that has a much more accurate positioning and a much more accurate hole diameter. And then we're going to be looking at a method where we have very high positioning and very high accuracy on the hole diameter. And one final last 4th way, well, we're going to be looking at extreme precision. So let's start at the start with our least accurate method. When we're positioning holes with low degrees of accuracy, well, we're going to be following the classic sequence that we followed in or on our drill point gauge project, and that was layout work, so laying out the positions of the holes, prick punching, center punching, and then moving over to the drill press for the drilling. Now, if it was a small diameter holes, so smaller than 1/4 inch, well, we go from the center punching directly onto the drilling. And if it was larger holes, so 1/4 inch and larger, well, we'd go from the center punch to the center drill or spot drill, and then to our final drill. Now, what could be expected with this method? Generally, if you do it attentively, if you pay attention to what you're doing, you can attain with this method on a drill press, well, about a tolerance of plus or minus a 64th. So if you prefer plus or minus 15 thousandths of an inch, if you get good at it, 10 thousandths of an inch. But that's pretty well the limit of what you can expect to hit every time. So not terribly accurate, but for most inaccurate jobs, it is by far the best method to use. It's quite quick and it's easy to do on a regular drill press. So for an example of that, we'll look at a sped up or a broken down sequence of those operations on our drill point gauge project. So it all starts with the prick punching of our positions. Note that we're using a small ball peen hammer. That's followed by center punching, and in this case, well, you can hear it, we're using a much larger ball peen hammer to enlarge the indentations. Once that's done, we can install our part into a drill press vise and install our first drill in our drill chuck. Note that we're not using a center drill here. Since the drills that we're using are smaller than 1/4 inch, the center punch mark is large enough to guide the drill to its proper position. This project consists of several holes of different diameters, so we can run through all those different drills, then we can pull the part from the vise and deburr the holes. The second method, well, is going to be a little more accurate and a little more involved. We're going to be doing it on the mill, it won't be on the drill press. And for this second method, well, you're going to need very accurate reference surfaces, because if you're going to position a hole accurately, it's going to have to be positioned from something that is accurate. So we have nice square and accurate reference surfaces that we're going to edge find with an edge finder or another method. And once we've set our axis 0 to those two reference surfaces with our edge finder, well, we're going to move numerically to the position that we want to produce our hole at. Now, we can do that either with the dial on the lead screw or with a digital readout. If you're not big on dials on lead screws, well, here's a little video that'll help you to get a little more productive and acquainted with how to use the dials when positioning holes. Now, this is an accurate method, so we're going to be, once we're at position, we're going to center drill or spot drill, and then we're going to drill, and then we're going to ream. And that final reaming operation is going to give us much more accuracy as far as geometry goes. It's going to give us a nice round hole that is of a proper and accurate diameter. Now, with this second method, we can still perform a layout, but we won't be punching the hole positions because that will draw our hole off its coordinates. I don't want to do that. I'm going to lay out if I want to, and I often suggested to students to do so. I'm going to be laying out a safety layout. I'm just going to be marking the positions of the holes without punching them. Why would I want to do that? Well, if I make a mistake in this type of positioning, it's usually a big mistake. It occurs more often than not during the edge finding process. And if I move over to my first position, let's say, in X and Y, and I just come and touch the surface with the center or spot drill, I'll see quite quickly if I'm in the right place, as long as I have a safety layout. So it's really just to see big mistakes. You can't see a thousandth of an inch with a safety layout. So here is an example, a condensed example of this approach. And it's the approach that we used on our 1, 2, 3 block project. So let's take a look at that.
This method obviously relies on the fact that you have a good square block. I mean, if the block isn't square, there's no use to positioning the holes from reference surfaces accurately. So square up the block first. And as always, when you square up, safety dictates that the part be deburred. Now, we lay out accurately from our reference point all the holes that we need to produce. Now, if we're going to be pointing or center drilling holes from coordinates, well, the vise has to be well aligned. So align your vise properly. Remember, we have a video for vise alignment. Once that your vise is properly aligned, well, we move on to our edge finding. And again, we have a video on edge finding, so watch that if you want to learn more. We can then move on to center drilling to our coordinates, and once that is complete, well, we can move on to finishing the holes either on the mill or the drill press. It's important to note, and we saw this in our round column mill series, that moving on to the drill press does not dramatically affect the precision of the positioning of those holes, so either will do just fine.
The third method is a little more accurate still, and it is basically the same as the second method, but we're going to add something to it, and that is boring. I don't mean that I'm boring, well, I may very well be boring, but I'm not boring right now. But I might be boring right now. Anyways, you get where I'm going with this. Boring is a single lip cutting tool that does not follow the existing hole. Reaming follows the existing hole. Remember, we saw that a few videos back. And the boring bar will not do that. It's going to follow the axis of the machine. So if I do the same sequence as I did with our second method, and that is to edge find an accurate part, move over in X and Y to our coordinates for the hole that I wanted to produce, center drill or spot drill, then rough drill, but not as big, and then I'm going to finish the hole with the boring bar. And that will bring the hole to its proper position, because if my center drilled hole wavered a little bit and wasn't exactly within the thousandths of an inch of where I wanted, well, the boring bar will bring it back to its proper position because it doesn't follow the existing hole. Now, remember also that with this technique, we can combine the speed and ease of use of a reamer with the boring bar. And in that case, what you're going to do is a center drill or spot drill, drill, Then you're going to bore, but not to final diameter, and then you're going to ream to finish. And that just makes it a little easier because it's a little finicky sometimes getting a very accurate diameter with a boring head. If you recall, we saw a little bit of boring on this mill in a video I produced not too long ago, the drill press repair video. So here's a clip of that just to remind us what a boring head and a boring bar looks like on a mill. The fourth technique is even more accurate and even more finicky. It's not something that we do very often because we don't need, generally speaking, 10/1000ths of an inch accuracy on hole positioning. But if we were to do that, it would normally be performed on a hardened steel part. Okay, this isn't something that we do with mild steel or even on most of our non-ferrous metals. Why hardened? Well, because a hardened piece of steel can be a lot more stable. Because when you're talking about 10/1000ths of an inch, a scratch is all you need to throw yourself off. So you can see how finicky this gets. And here's how it goes. It follows basically the same operations that we saw in the third technique, but we're going to replace the boring head with a planetary grinder. So in other words, a boring head that has a grinding wheel mounted on it that's going to grind as it moves around the axis of the hole. Now there's a final approach, but it's important here to follow the sequence. If this is to be done on a hardened part, well, you're going to have to rough mill the reference surfaces. Then position your part with taking into consideration the over dimensions on those surfaces and come and position your hole. You're going to do what we basically have done up to now is center drill, spot drill, and drill. Center drill, spot or spot drill and drill because you have to rough that hole out because the part needs to be hardened. You can't produce the hole once it's hardened easily anyhow. It is possible, but it's not easy. So you rough the hole out and then you move on to the heat treatment. The part is heat treated, then you come back for external grinding. You got to establish your reference surfaces. And once that is done, well, you're going to set up on your jig bore, is what I used to use years ago, and today, well, it would be a very, very accurate mill, not something like this here. And you would install your grinding head and set up and come and planetarily grind that hole. That would be very accurate as far as diameter, as far as geometric shape, and as far as positioning. But if you needed even more accuracy in positioning, you can add a final step to that sequence, and that is when you grind the outside surfaces of your part. I tend to leave about a 1/2 thousandths or 5/10,000ths of an inch on my X and Y surfaces, if those are my reference surfaces that I'm using. Then I would come and position my hole taking into account that over dimension, really position as well as possible, finish my hole, and then come and adjust the final position by grinding on the surface grinder those two reference surfaces, that final 4 or maybe 5/10,000ths of an inch, to just bring it to its very, very accurate position. So that would be another way to go about it. Now, a lot of these techniques can't be done on a drill press. So why am I talking about them here? Well, because I have to talk about them somewhere, and I don't want to do half of positioning drills in the drill press series and another part in the mill series and another part in the grinder series. So I've sort of all condensed it here. Drill presses are important machines, and they are a staple in home shops, in any shop really. They're great machines, but one thing that they aren't is very productive when it comes to producing large amounts of parts. I mean, we've seen that really the way to go about it is either position center holes or spot drill holes on the mill and then move over to the drill press, or do some layout work, some punching, and then moving over to the drill press. Both ways are time consuming, but we can increase a drill press's productivity, especially and really only when we have several parts, identical parts to produce. And we can do that by producing drill jigs. I have an example here of a very simple drill jig. And before we'll look at this jig, well, let's take a look at the project that it was designed for. It all starts a few years back at school. As for every year, well, we did a final project that tried to group as much of the things that we learned as possible into one single project. And that year, well, we decided to produce a fishing lure. And the first thing that we had to do, well, was to produce a punch and die set to produce these blank brass parts. Once that was done and the parts were blank, well, we had to drill 2 holes. And we produced that a drill jig, and that's what we produced it for, to produce 2 holes in the blank parts. Now, once that was done, well, we moved on to engraving the lures and giving them in a rolling setup their twisted and curved shape so that they would jig through the water. So once that was complete, well, we kitted them out with treble hook and a little eyelet there to hook it onto some line. And that produced our fishing lures. And that as such is not really important, but what we want to get to is the drill jig. So let's take a look at how that drill jig increased our productivity. So here we have our drill jig, and it's made in 2 large parts. And there's more than 2 parts here, but there's 2 parts that separate during use. And I can see that in the top part here I have a nest that has 2 accurately positioned holes at each end and this large center hole. Now this large center hole is used to extract the parts after the fact, so not really part of the drilling operation. Now this is a nest positioning, and that means that this cavity here is just slightly larger than the parts that need to be inserted into it. And what does that mean? Well, that means that this is a couple of thousandths of an inch larger in every dimension than the largest possible part here. What's the largest possible part? Well, this part at its maximum tolerance. So I can produce with this tool 5 parts at a time. So let's insert these parts into the drill jig. Put the base on. We're working upside down for mounting the base, which is a normal thing. Now normally I would have used shorter screws or even some type of cam action screw to accelerate the assembly process here. But this is a home shop, so we're going to keep it simple. And then we can flip it over and see that we have 5 parts inserted inside this jig that are properly and accurately positioned in relationship to these 2 drill bushings. Now these are hardened and tempered drill bushings, meaning that they have holes in them that are just slightly larger than the drill that we're going to use to drill the holes in these blanks. So let's take a look at what this looks like when we use it over on the drill press. So I'm set up here, and what have I done? Well, I've set my RPM to the proper RPM. I've mounted my 1/8 of an inch jobber drill bit in my drill chuck here. I've set the depth stop so that it just comes down slightly below the intersection between the top and the bottom half, or in other words, just barely through the part. I don't need to go any further than that. And importantly, I've mounted a stop here, something against which I can lean my jig here when I'm drilling, so that this jig doesn't start spinning around should the drill jam into one of the parts. And that's crucial, and you want it to be leaned up there. You don't want to clamp your jig to the table. You want it to be loose. That's how it's going to adjust its position when the drill is in the hole. It has to be floating there. But you do want something to impede the rotation should something jam. That's very important. And finally, I've got my safety glasses. I'm getting up close and personal here. You'd be surprised at how many people get right in there and don't wear these. I mean, this is important. Okay, so wear your safety glasses. So we're ready to rock and roll. So let's bring the camera in a little closer and we'll drill those 10 holes. So that went really well. I got 5 parts completed in under a minute. So I mean, that really increases productivity because it speeds up the cutting of this project. Now, if I had 10,000 of these to produce and I used this jig instead of producing them one by one, well, I would only have 2,000 setups to produce here. But there's the time you save when you're cutting, and then there's the time that you save when you're not doing something else. And what I mean by that is, if I use this jig, I have to pay particular attention to accurately laying out and producing 2 holes once. And that's when I produce this jig. After that, there are no more layout operations. There are no more punching operations. Because, let's be honest, if I were to produce these one at a time, I would have 10,000 parts to install on my drill press. I would then, before that, have laid out 10,000 parts and punched 10,000 parts. That would have taken an incredible amount of time. So we can see that a simple jig can really speed things up and make us a lot more productive. But it does something else also. I mean, what it does else is it ensures a higher degree of accuracy. These are very repeatable tools, so I'm going to produce part after part after part, virtually identical and well within their tolerance because I've set up my jig properly. So we can see that there's a real advantage to that. But a jig of this type that takes a couple hours to produce, well, probably isn't worth making if you're only going to produce 10, 20 or 30 parts. And if you are, well, is there something that we can do? Well, yeah, we can make a poor man's jig, and we'll look at an example of that now. And for that, we're going to be using this plate as an example imaginary part that I have to produce. And let's say that what I have to do here is drill a 3/16 hole into this plate. Why? Why not? It's just an example. So let's take a look at what we can do for a poor man's jig.
Hey Mark, next time try turning off the radio. So here I'm laying out my position from the reference surfaces, and now I can punch that position. I'm going to start with a prick punch, and with a prick punch I'm going to use a light hammer. I can adjust its position because it's important that this hole be positioned accurately, since the position of this hole will determine the position of all the other holes that I'm producing. Once the hole has been prick punched, I can move on to my center punch and enlarge that indentation. And for that, well, obviously I'm going to use a much heavier hammer. And there you go. So I have my part properly mounted in a vise. It's free to move, but I have a stop on the table to lean up against, and I can position my drill for drilling this hole, and then drill the hole.
Okay, so what do we have here? Well, we have our part with its pre-drilled 3/16 hole in it, the one that we want to reproduce on other parts. And what we're going to do here is we'll drill 4 of those holes, 1 in each corner. And we have our 3/16 drill, but we also have a clamp to hold the part onto the table. And we have these 2 parallels that are going to serve as stops. Primary is going to be the table, secondary is going to be this parallel, and tertiary positioning is going to be this parallel. We're going to be using isostatic positioning here now. If you don't know what that means, here's a video that can help you out. It's really something that's fundamental to positioning parts on machines. And well, obviously I have my 2 finger clamps here. So what I'm going to do is position this part so that it comes, our hole is, here, I'll get it here, there you go. The hole is over the drill, okay? I'm going to clamp that down. So my part is in position. Then I'm going to bring this back parallel up to my part. There you go. Just position it snug for this for now. And come and use the corner of this parallel for my tertiary contact point. Now, this is fine. I could drill here, but the drill is going to wander. I want it to track properly. And important here, I don't want to have to center drill each hole. I'm going to be making about 50 of these plates for my brother-in-law. It's an imaginary job. So what I'm going to do, well, I'm going to use this piece of mild steel to produce a guide for me. And I'm just going to slip it under these 2 finger clamps here. Just position that. It's nothing here is crucial. It doesn't have to be pretty in any way. So there, okay, I have contact here, I have contact there. Now I'm going to have to snug down. Snug, contact, and tighten. Okay, good contact and tight, and do the same thing over here. Snug this down. Make sure that I have a good contact. There's a good contact. And tighten this one down. Okay. So I have contact point, contact points, and my primary contacts. And I have this bar of mild steel that I can drill through, and it will serve as a guide to help me afterwards with the drilling of the other holes that I have to produce. But the drill is going to wander here. I want that to be positioned properly. So what I'm going to do, I'm going to swap out this 3/16 drill for a center drill the hole, reinstall my 3/16, and then we'll be good to go. So we're all set up and ready to go, but I can simplify this a little more because my primary surface isn't going anywhere, my secondary surface isn't going anywhere, and my tertiary surface isn't going anywhere. I mean, I've blocked the rotation, and the only thing left, well, is the Z-axis movement possible of the part, but my guide plate here is blocking that axis. It can at best come up by 1/8 of an inch. And that really doesn't worry me at all. So I can simplify this setup now without moving the table. I can't move this table in any way, shape, or form from here on in, but I can get rid of this clamp here. It's just not required anymore. So I'm going to get rid of this, and then we're going to start to drill. Well, that's about all that I want to do in this lesson 8 on the drill press. We could keep going, but really this is lessons for novice machinists, so we're going to stop it here. What's coming up next? Well, probably lesson 9, that's going to be about the lathe, unless I decide to do a project in the meantime. We'll see. It's for fun, so I take it pretty well as it goes. That being said, as always, until we meet again, have fun, be safe, and happy machining.